our t-distribution. So our t-distribution is usually the common way for us to actually take a sample and try to view and figure out what, if our sample follows the population, and how likely is that we actually, quote unquote, caught the population mean. Because, then if we know we caught it, or if we're pretty certain that we caught it, then we can kind of do a lot more, say, okay, well, this sample, even though it's not the population, we can still say things about the population based on this sample. It's representative, okay? Kind of some fun facts about the t-distribution. It's actually called the student's t-distribution, but it was discovered by William Gossett in 1908, who actually worked for Guinness Breweries. So same Guinness who makes beer today. And what's interesting is that as a private company, and he basically came up with this technique of trying to find, I can't remember the exact details, but basically he was literally trying to make better beer. And so he's a statistician, and he basically discovered this method, using this t-distribution. There's a few other distributions he kind of come up and coin and stuff like that. But you'll hear it called the student's t-distribution and not like the Gossett t-distribution. And that's because when it was first published, Guinness said, like, you can't publish under your own name because, essentially we own you. Like, that's kind of like their view. And so they actually, he said, okay, I'm going to call it the student. I'm a student. And so now it's the student's t-distribution. But a lot of times now we'll call it the distribution, not distri. Wow. I can't spell that way. We'll call it just t-distribution. It means the same thing, okay? So again, we do this when we don't know the population distribution. We don't know if what the population actually looks like, but we assume for the central limit theorem is that with a large enough population, we likely will have a normal curve, just because the central limit theorem basically says, as we get more and more data, there's some random variables just kind of even out, and we end up getting a nice bell curve. Okay, so you'll notice real quickly is that this is from the curriculum too, is that blue right there is the normal curve of this particular, settings and stuff like that. So you can see there's a nice normal curve is that blue, and that red one is our t-distribution. And we have something in t-distribution called the degrees of freedom. And basically it describes, it's a little subtle exactly why we call it degrees of freedom, but basically it's the different ways the data can vary, if that makes sense. So like the more independent ways it can vary, the more degrees of freedom. And usually that comes down to the fact of just how many you have in the sample. So if your sample is like 100, you basically have 99 ways that those other people can be varied throughout the time. And you can kind of think of like when you say varied, like it's like, oh, independently varied, is that you can think of like that ball can drop down into many different ways. And if we have more and more balls, basically, we have more degrees of freedom, more ways that ball can vary throughout, taking that sample. So usually people, to be honest, will kind of skip over degrees of freedom and just say, oh, it's just like 1 minus the sample size. But just know that it's just the number of ways things can vary. And this will come in play when we have multiple, when we're looking at different kinds of populations and stuff like that. So just know it's just the number of ways things are varied. So as we basically increase our sample size, we're more likely to have a normal distribution, right? So as you can see, the degrees of freedom increase in this graph. Each time the red one is the newest one, and I think they keep the green ones as the previous ones. So the 1 degree of freedom, you can see, well, it's kind of normal, but you can see these tails carry a little more weight. Basically with one person, right? Like one sample, or let's say even 2 samples, you're more likely to end up being in this tail area, right? Because they can, they're most likely to still land in the mean or the real population mean, but they can end up being here. And since you're only looking at 1 of them or 2 of them or 3 of them, they're just more, they don't balance out, if that makes sense. Okay. Any questions on that? I heard someone.
So the t is a function of the actual sample, right? And it's just be compared to a standard normal distribution.
Right. Yeah. And when I say like t, this is like we're assuming our sample distribution will look like this. That's kind of like the idea. And so we can't directly, if we get a sample, for example, and we get our mean, we can't actually assume the normal distribution. We basically say, well, at this point, if we continue with this probability of people, we would get a t-distribution. And so that's kind of like what we do the statistics on. Instead of doing statistics on the normal curve, we use a t-distribution. But we also adjust for the fact that it's like as we get more and more in the sample, our t-distribution will get more and more like a normal curve. Did I answer your question?
Yeah.
Okay, cool. So yeah, so you can kind of see as we increase our sample, basically that red curve becomes more and more approximate to the normal curve. And you can see after 30 degrees of freedom even, we actually get pretty close to the normal curve right here. And this is just a mathematical formula that we're assuming, like basically we're saying, okay, we're gonna test it on this distribution to make sure that we're not actually using the Gaussian, or not Gaussian, the normal curve, okay? So this kind of leads us into something called the confidence interval. So the confidence interval really just says, you guys might have heard this already, like, a confidence interval will be like 95% confidence, or a confidence interval 95%. And it's kind of a subtle point of what we mean by a confidence interval. And sometimes you'll hear people, like all the time in statistics, just like I talked about in the p-value before, sometimes it's just quoted incorrectly. And it's just one of those things where it's like, like it kind of hurts me a little bit when I hear it. But just know that for the confidence interval, what we really mean by that is saying how confident we are that when we test it over and over again, like we'll get a sample mean, for example, right? So we'll get a sample mean and we'll say, okay, we got a sample mean of, let's say, 30, right? 30 years old, and say, how confident are we actually landing in that zone? And basically a confidence interval says, okay, well, if I want to be quote unquote 95% confident, there's this range from here to here. And basically it comes down to the fact that if I were to do multiple samples, let's say 100 samples, and calculate their confidence interval of their different distributions. So sometimes the distribution will be right here, sometimes they'll be off to a little smaller, sometimes they'll be a little bit bigger. But basically, if I did that 100 times, 95 of those confidence intervals will contain the population mean, which is the thing we don't know, right? So it's a little subtle. Sometimes people will say things like, there's a 95% chance of us catching the population mean within our confidence interval. And that's not quite right. That's not, because the population mean is the population mean. It doesn't change, right? So it's not like the population mean might 5% of the time be somewhere else. It's much more that with our sample that we had, if we were to keep doing samples, our confidence interval with this size will catch the population mean 95% of the time, okay? It's a little subtle and stuff like that. This is like statistics stuff where you'll hear people talk about things and, it's kind of a different terminology. But what's kind of nice is that we can actually calculate this interval and say, okay, what does that interval size look like? And for example, we want a confidence interval of 95%, which, just so you guys know, kind of corresponds to a p-value of less than 0.05, okay? So that's kind of actually where it comes from. So if you were looking for more p-value of, let's say, 0.01, your confidence interval would be 99, okay? That's kind of what it's coming from, all right? So, sorry. So let's do some calculation on this part. So if I actually run this right here, so I get basically SciPy stats, and this comes from a lot from the curriculum. And basically I say, okay, my confidence interval is 95%. Okay, that's the confidence interval I care about. And then what I'm going to do here basically is I'm going to take, it's going to give me from this stats t interval, it's going to give me the start of the interval and the end of the interval, kind of like these braces right here. I'm going to say, okay, given this information, our alpha is basically our confidence interval. So it's kind of like the opposite of p, like 1 minus p. And then basically number of freedoms. So basically if I had a population or a sample size of 100, my degrees of freedom would be at 99 in this case, okay? And then in this case, I'm just giving something random. Like, okay, let's say my sample mean was 65, and then my standard deviation is 18. You would actually get these from like actually doing your sample. I'm just making them up just to show you an idea. So like I did my sample and I find out, oh, the average, let's say age is 65 and a standard deviation of 18. So it's like, okay, it means it varies in there. And standard deviation estimate, meaning like the sample standard, the sample deviation, the sample error, okay, that S, lowercase s. And so I can run this part right here and I get now this interval. And now I can say, okay, to get 95% confidence interval, I need to look at an interval that is from 29 years old to 100. Note that's a really big range, but that's because we're trying to be 95% confident. If, this is an extreme part, you normally wouldn't have like a 60% confidence interval because then it's like anything goes. But if I have this, you can see my confidence interval will get much smaller. But I'm only 60% confident that my intervals will contain the sample mean or the population mean, okay? So again, this comes from the curriculum. It kind of goes through a bunch of it, but I'll kind of give you an example of data that again kind of comes similar to the curriculum. So this right here basically will allow us to randomly generate along a normal curve some samples. So this right here, basically, it's like, okay, this is what the mean will be. This will be the standard deviation. And this is just the number of samples I have. Okay, I'm sorry, the number of samples I'll have, right? So I'll get, this case, 10,000 individuals, okay? So if I do this now, I now have a whole list of all these different samples, right? In this case, I'm just going to convert into a data frame. So I'm taking that sample, turn it into a data frame, and then I do a histogram. I'm just going to bin it by 100, so that means we can see it. If I don't do 100, if I just took this part out, it might be more blocky and it might not be as high resolute. So I'm just putting 100. I could put more too, but 100 is pretty good. And I'm doing a range from -20 to 120, just to give us a large range. Remember, it should hit about 54 is what that average should be. Okay, so I go ahead and run this part, and you can see now for this specific sample, right? I have, 10,000 we had before. We have our population, our sample mean, 53 years old, which you see is pretty close to 54, right? Which makes sense. But it's not quite. Where our standard deviation in this case for the sample is 17, which is almost exactly what we had, populated in here. And then we actually have, our normal descriptive statistics, 25%, 75%. So basically 50% of the population, our sample runs between 42 and 64. And we can actually calculate then, before we do a calculation, you can actually see this is the distribution. So you can see most people land right about here, which makes sense. But you can see sometimes there's little peaks right here. It's kind of varied. Some people get really far off to the side here. Some people are negative. This is not a realistic data set, but like we're just kind of playing around with it, right? And so we can actually calculate this standard deviation, or our t interval, or our confidence interval from the t statistic, or t distribution. So we can see here, I have just the samples -1, our sample mean, our sample standard deviation. And so if I run this now, you can see that it goes, oh, from 20 to 87. Basically, that would be about, we would expect 90, or if we kept repeating this again and again and again, that interval would catch the population, catch the population mean within that area. Just to kind of give you guys a little bit of example, let's say I do like something like 500. 500 samples, right? Which would be much smaller, right? So notice that I put 10,000, that's pretty close to a normal curve, right? But if I only do 500, you'll see that it doesn't quite look like a normal curve. You can see it's kind of skewed off to the left here. That's random. You can see that the mean's still 54, standard deviation 16, but now we have like kind of a much more, like wonky distribution. So we're not sure how close this actually relies. So in order to get that same 95% confidence interval, you'll see that this part right, oh, I'm sorry. This is actually because it's the same, we're using the same size of the population, right? So we'll get very similar numbers to this part right here because, let me make sure I have that right, yeah. Because basically it's our t-statistics of saying how big it is. But if we had something very, very small, like 50, and then you can see, for example, really varied, right? Like it's hard to say like if that's normal or not. We can see our confidence interval get larger. See, it went down to 19 and 88. And basically this t interval is independent of, like, in a way, independent of the actual specific points. It's just saying, all right, if you have a specific standard deviation, or standard deviation for the sample mean, and then a specific degrees of freedom, this is the interval that you have to use to get that 95% confidence. Okay, cool. Again, this is kind of like some stuff, in my opinion, can take some time to kind of get used to, like what exactly we're testing out, and like understanding, like, okay, like I have this sample, and then what am I doing with this? And the main thing you're trying to do, your main goal is basically saying, how well does my sample represent the actual population? And that's what we're really talking about when we're talking about a t statistic, our t interval. Our t statistic is very similar in the sense of our z statistic, or z-score, if you guys remember that from even mod 1. The curriculum actually talks about it in here too. But the z statistic, the reason why we don't using z statistic is because that relies on the fact that we have a normal curve. But we don't actually know that for our sample, because we don't know what the sample, or sorry, the population mean, the popular standard deviation is. So our t statistic basically allows us to use the information just from the sample to predict what the population mean, and basically what the population actually looks like. Okay, cool. All right. Any questions on any of the stuff I talked about? Cool. All right. So thumbs up, thumbs down, sideways on understanding Like, maybe read it some more. Okay, cool. See some thumbs up, sideways. Yeah, that happens. And honestly, I always say, like, it's never a bad thing to be sideways. It's not even a bad thing to be down, right? Usually it's down means that I did a really bad job explaining things. But when it's sideways like this, it means like, okay, I need to kind of review it a little bit more, and obviously I only have so much time to talk about all the information that the curriculum gives. And the curriculum, as you kind of saw, has a lot of dense math, and it does have some coding more towards the end of showing how to do using a sample, sampling itself. So I would really focus on, what was it? This part right here. I'd say make sure when you walk through this part, make sure you really go through and check this out and see, what this looks like, and see if you understand each step of the way, because that'll help you understand when you're doing sampling, what you're trying to achieve. Okay, cool. So I'll go ahead and stop sharing.